committee is complete here on the spot. The videos are online, so we can start. I will start with a few remarks on the organization. Then we will have I will introduce the committee, of course. We will have a 20-minute presentation. And then we have the reviews. Each reviewer has time to present his review. It's not necessary to read it all, just summarize it in a balanced way and address the remarks and questions in your review. I have somehow to assign the order. So Professor Jančar, who is here present in the room, will start with his review. It's relatively shorter. And then I ask Dr. Aragon Camarasa and Dr. Haške to continue. Each of you will have enough time to do the examination. Then we can have a discussion committee-wide in which everybody, not only the reviewers but also the members of the committee, can ask questions with the aim to determine if we can actually vote positively for the thesis to be defended. After these, we'll have closed session without any external audience. So if you can see there is some audience in the Microsoft Teams meeting. They will have to leave, or I will have them leave. We can discuss internally before we vote, and then there is a secret vote. All of you have seen the link, so it's as easy as clicking your choice. After all of us vote, we'll see the results immediately, and then according to the rules, we will proclaim the result, basically a recommendation to the dean, either to accept the defense or not. We are 7 voting members, so if at least 4 are positive, the defense is successful. So, if now regarding the Microsoft Teams, there are some mechanisms which we can use. We can use the chat, of course, to give me feedback silently for each other. You can also raise your hand if you know this tool. It's on the main toolbar. If you raise your hand, then you call my attention, hopefully. Maybe you can try it now, just for you to find where the tool is. So, if you please raise your hand, and not physically, but using the tool. And it's on the main toolbar. 1, 2, 3, 4, 5th icon. All right, perfect. I can put you down. Now, if you want to see a concrete participant, you can pin him. So, if you go to the people, the participant tab, click only on a person, you can pin him or her, and then it's he or her will be permanently visible. Otherwise, you only see 4 people speak, those who speak. Yes?
I have a remark. So I cannot access the chat, and I don't have this main toolbar or whatever, so I cannot raise my hand electronically.
You did somehow.
No, Gerardo did.
Okay. Maybe someone else, because the order here is changing. It's a bit anyway, if you just speak out if you need. I think we can manage. Yeah, there is, if you can access the files, if you go to Teams, open the team, then there is
So,
General Post Files tabs on the top, and under Files you see the files which is the presentation, reviews, the thesis itself. I think I've sent you an guidance. Of course, you don't vote until I ask you to do so. So please, it's now not possible, but it will be possible in about half an hour. But we don't vote until we have this closed discussion. Okay. So what we will have to do by our bylaws require that we record all the defense, excluding the closed session. And we also stream it to the external audience because not much audience is allowed in the room. So the open public parts of the defense, including the reviews and questioning, will be broadcast on YouTube. And I guess you agree with this arrangement. If not, we have a problem. So what I will do is I will start, are we broadcasting? Okay, I will start recording for offline for our internal purpose. That's like a documentation that the defense went as required. I actually have a cheat sheet here with 18 points to go through, so I'm at point 2. Okay, so let me welcome Jan Stria, who is the candidate today. He's defending on visual perception of garments for their robotic manipulation. As I said, the thesis is online, and we have the thesis physically here for the other members of the committee. The supervisors are both here. Professor Václav Hlaváč is the main supervisor. So thank you for coming, Professor. If you say something, it will be heard, so both of you can speak. Pašek will later introduce the candidate. And Dr. Daniel Kusha, who is also here. I know that you worked together at the beginning, but I'm not sure how much. Okay, how much?
2 years.
Anyway, you are here, and we are happy to have you here. We have 3 reviewers, now all external, so I will list you in the order in which I would like you to present your reviews. So Dr. Petr Jančar is from Palacký University in Olomouc, Czech Republic. He's a professor at the Department of Computer Science. Welcome, thank you for coming.
Hello.
Dr. Gerardo Aracon Camarasa, who is remotely at University of Glasgow. He's a member of Autonomous and Socially Intelligent Robotics School of Computing Science. Welcome. Thank you.
Thank you.
Okay. Dr. Robert Haschke, who is also remotely from University of Bielefeld, Germany. He's the head of robotics group at the Faculty of Technology. So, welcome, Dr. Haschke.
thank you. Hello.
We have a few more members of the committee besides myself. I think I have not introduced myself, sorry for that. My name is Radim Bishara. I am local from the Department of Cybernetics, Center for Machine Perception. Then Associate Professor Barbara Zitová, who is, you may see her behind me. She's from Czech Academy of Sciences, where she's heading the Department of Image Processing. Welcome. Associate Professor Miloš Železný, who is present here from Slovenia University, Pilsen, is from the Department of Cybernetics here. Thank you for coming. Hopefully your parking was not difficult. Your parking was smooth, hopefully.
Everything was smooth.
All right, thank you very much. And Dr. Matej Hoffman, who is sitting next to me, he's also local from the Department of Cybernetics. He's a roboticist. So that's the introduction. I can see that there are a few more people in the participant list. Jiří Sedlář, who is an audience, and Posádka, who is technical support. So Mr. Sedlář will have to leave for the closed session. Okay, so number 6 of my cheat sheet states that there were no comments received from outside, so it's possible to object or comment on the thesis to the committee. Nothing like that happened, so we don't have to include that in the proceeding, and we can have the regular procedure, which basically starts with the supervisor introducing the candidate first. So if you are ready, Vašek,
Yes, I'm ready.
then please speak loudly and say a few words about that.
So I had the privilege to be a supervisor of Stria from September 2012, a long time ago. Dr. Daniel Prusha, who is sitting close to me, helped me as a second advisor, mainly at the beginning. Stria joined the Clothes Perception and Manipulation project, which ran from 2012 to 2015, where the motivation for the thesis came from. Stria is a PhD student. Stria combines passion for research, mathematical formulation, excellent software development skills. We dealt with recognition of handwritten mathematical formulae at the beginning. Our initial results were encouraging. He published 3 contributions on the topic. We also scored quite high in competitions. Our main competitor, the academic and commercial team from France, became much better in competitions in 2014. May I shorten it a little, Radime?
No, it's okay.
It's okay. So we gave up, and we found another topic which was related to project we were working on that time. Stria has designed, implemented and tested, published several novel methods. He has been working hard, efficiently, and progressed well towards the goal. He published continuously. He could be faster though, 2012 we started. Nevertheless, the slower speed is well compensated by thorough work and results. In my opinion, Stria has been also contributing to our lab significantly by helping others with mathematical background, software issues, and by teaching. Research. Stria efforts contributing to his PhD have been oriented to image analysis related to garments. There are 3 main contributions, and I'm not going to read it because it's going to be repeated today several times. Stria published in good conferences and a good journal paper. In my opinion, Stria original research results and his PhD thesis text provide sufficient evidence of the scientific merit and originality. It enables me to recommend the thesis for the defense. So that's what I wrote on October 2nd, 2019. Maybe I'll also mention that Stria succeeded in a harsh competition for the position in Google Research, where he's working right now in Berlin, where he's working as a research engineer. Mr. Chairman, I'm finished.
Thank you very much. So you could hear that the thesis was actually submitted October last year?
September.
September last year. There were some delays. We should take this into account. Regarding the state of the art, we cannot compare it to the state of the art in some methods. So please be kind from this point of view. Okay, thank you. So I guess we have time for the presentation. I give you like 20 minutes, plus minus few, to present your work, your results, in single
Okay, thank you.
floor.
Thank you for the introduction. Today I would like to present you my thesis on visual perception of garments for their robotic manipulation. In my thesis I dealt with 3 different topics. First one is visual perception of garments for their robotic folding, which you can see on the left. The other one is visual perception for robotic unfolding, which you can see on the right. And the third one is classification of hanging garments. So let me start with the visual perception of garments for their robotic folding. This task can be formulated as follows. On the input, there is a single image of a garment, which is initially spread, and whose category is known in advance. The task is to recognize pose of the garment by fitting a model to its contour, to its outer contour. And the vertices of this model correspond to significant points on the contour, like armpits, shoulder, armpits, corners, and so on. Based on this fitted model, it's possible to plan a folding axis, fold the garment, and then repeat the procedure for the folded garment using a folded model. The whole procedure starts with segmentation. We assume that the background of the garment, basically the table which the garment is laying on, is known, it's more or less invariant, and it's dissimilar from the color of the garment. This makes it possible for us to learn a probabilistic model of the background color. Then, while we are presented with the input image, each pixel of this image is evaluated in this model of background color, and high likely pixels are labeled as background, low likely pixels as foreground, and others are labeled as unknown. This coarse segmentation is used as initialization of a GraphCAD algorithm, which provides the fine segmentation, which you can see here. This is the initial coarse segmentation. This is the final segmentation. Normally, the GraphCAD algorithm needs user input. It needs user to provide these samples of background or foreground pixels, and we can do it automatically. Once we get the segmentation mask, we extract contour of the garment out of it, and we approximate it with a polygon, which has 10 to 20 vertices. The contour of the garment is modeled by polygonal models. There is one model defined for each category of garments, so model for towels, shorts, pants, and so on. Vertices of this model are defined manually, and they correspond to this important point on the garment contour. And relative positions of the vertices are learned automatically from data. We learn distribution of inner angles adjacent to individual vertices, and we also learn relative edge lengths of this polygonal model. You can see that some of these angles are labeled with the same label, this gamma here. It means that the distribution for the right armpit and the left armpit are shared. By doing this, we model symmetries of the polygonal model of the garment. We simplified contour, which was extracted from the segmentation mask, is then mapped to this polygonal model of the contour. You can see here, these are the points on the left of the simplified contour, and this is the polygonal model. There are more points in the contour than is the number of vertices in the model, and that's because while we are approximating the contour with the polygon, we do it in uninformed way. We don't know where the vertices should be, so we rather approximate it with more points, and then we match it to this model. Each mapping of points to vertices is assigned certain cost. We use 2 different sets of costs, local cost, which leads to a simpler matching algorithm, and more complex global costs, which require more complex mapping algorithm. The local costs are based on cost paid for approximating this part of the contour with this model edge. And also there is a cost for mapping point Pj to vertex Pm. So this cost Pjm. And this is based on the likelihood of this angle in the learned module of the inner angle adjacent to this vertex. The global cost, they also have this include this cost for approximating part of the contour with model edge. There is more complex vertex matching cost. It's basically cost for matching PJ. Sorry, it's cost for matching point PJ to vertex VM, provided that the point PI is matched to the previous vertex and PK is matched to the next vertex. And there is also cost paid for comparing this observed relative length with respect to this length of this whole contour with this learned relative length for the model.
Maybe say a few more words about each thing because the pointer is not visible in the transmission. So you can see it here, but they don't see it probably.
So
each time you explain something, say it in full.
Yeah. So
middle, figure, etc.
Yeah, so on the left there are those local costs. There's this in the middle. This is the so on the left there is, and on the right there is this polygonal contour, and in the middle there is this vertex model. As I said, this matching procedure is used at the beginning for the initially spread garment, but it's also used after folding it over this planned folding axis to check the pose of the garment after each fold. The garment is matched these polygonal models, which are derived automatically from the initial polygonal models. These partially folded models, which you can see in the presentation. Here is some evaluation of the both procedures. So we tested it on 290 samples. You can see that the local matching failed completely in four cases, meaning that the matching was completely nonsense. On the other hand, the global matching succeeded somehow in all the cases. Of course, there is always some displacement of the matched vertex predicted by the model and of the ground truth given by the annotator who clicked the positions of these important points in the image. The procedure, the visual perception procedure, was also deployed to the real robot, and here you can see robot folding a t-shirt, and on the right you can see the whole pipeline for unfolding and then folding garments, starting from and making it folded. So this result was integrated in this pipeline together with results provided by other members of the Clothemart team, which was mentioned here. The second part is visual perception of garments for their robotic unfolding. So here, the input is a garment which was initially spread, but then it was folded by grasping its contour and or outline and bringing it towards the center of the garment, as you can see on the left image. We acquire single image and single depth map of this garment. You can see the depth map in the middle, and the goal is to detect the top folded layer. There can be more folded layers. We allow more folds as long as they don't overlap. And once the top folded layer is detected, we would like to predict or detect the folding axis to be able to grasp the green. You can see it on the right. So the green layer is the folded one, and we would like to unfold it over the folding axis instead. The input image is again segmented with the same segmenting procedure which I presented before for folding, and the input depth map is preprocessed by by estimating the plane of the plane going through the surface of the background, and this plane is subtracted from the depth map. By doing so, we get for each pixel estimated height of it above the table. The detection of layers is formulated as pixels labeling problem. You would like to each input segmented pixel. You would like to assign a label Z, which can be from the set T and B, which means top and bottom, whether the pixel belongs to the top or bottom layer, as you can see on the right page. The labeling of pixels combines information provided by image and provided by this height map, which was computed from the depth map. It is based on two. So the combination. Basically, we would like the boundary of the layers to be coincident with the edges seen in the image, because there should be edge between the top and bottom layer. And we would like the pixels from the top folded layer appear higher in this height map than the pixels from the bottom layer. So this is how we combine the image and that information. And we formulate this as pixels labeling problem, or as an energy minimization problem, which is quite standard in computer vision. The unary potentials are based on these pixel heights, and basically the unary potential of pixel belonging to the top or bottom layer is based on likelihood of it being the part of the top or bottom layer based on the heightness. So we basically model height of the bottom layer, and we model the height of the top layer with two normal distributions, and we use these distributions to compute the cost of matching the pixel to the particular layer. What is quite interesting here is that of course each of these distributions has some prior. They have a shared variance which somehow corresponds to the noise in the depth, and their means are linked with this relation that the mean of the top layer should be twice the mean of the bottom layer, because there are two stacked layers of the garment. So this is why they are linked like that. We use modified EM algorithm for. We modify standard EM algorithm for GMMs to be able to deal with this linked means, to be able, and we use it to estimate these means, top and bottom layer. So this is how we use the depth information. We also use the image information, and the image information. As I said, we would like the boundary of layers to be visible in the input image, and this is encoded in the pairwise potentials. And these pairwise potentials depend on the visual difference of neighboring pixels. So if two pixels are assigned to the same layer, then there is zero cost paid for them. But if there are neighboring pixels which are assigned to two different layers, then the cost is negatively proportional to, or inversely proportional to their visual difference. The energy function is minimized with graph cut, which is quite standard in computer vision. This gives us the segmentation which you can see on the image, and we greedily select the largest top layer. In case there are more top layers, we greedily select the largest layer for unfolding. As I said at the beginning, since the configuration of the garment was achieved by folding initially spread garment, the folding axis must form part of the outer contour of the garment. You can see on the left. So the green one, is the top folded layer which we detected, and now we know that somewhere on its outline there must be a folding axis. The folding axis should be approximately straight line or segment, straight segment. So what we do is that we approximate the outline of the stop folded layer with the polyline, and the segments of this polyline form candidates for the folding axis. Then we try to virtually unfold the garment over these individual candidates, and we check the virtually unfolded shape. We discard those virtual unfolded shapes which overlap itself, which is the red one, the third image, which is like heuristics for discarding some invalid configurations. And we also prefer unfolded shapes which are less complex. So in this case, the second image, the cyan unfolded shape, would be preferred over the last one, over the yellow one, which is more complex. This is just a heuristics which works in most cases, and when we do this because in this work for unfolding, we don't use any model of the garment, so we cannot there is no model of the garment used in this unfolding. Again, this method was evaluated on data set containing 13 different garments, each posting 15 different folded configurations. In the table you can see the results. The procedure succeeded in 87% of cases. In 11% of cases, the layers detection part of the procedure failed, and in 2% cases, we introduced heuristics on estimating the folding axis failed. You can see the failure of folding axis detection in the top right corner. It's obvious that it's wrong. Again, this procedure was deployed to a real robot and tested on different kinds of garments. They're able to unfold them. Finally, the third part is a classification of hanging garments. Here, the input are so we assume that the garment is being held by the robot. It's rotated around its vertical axis, and while it's rotated, we acquire multiple depth maps showing it, and we would like to use this sequence of depth maps to classify category of that hanging garment, which is quite important prior to any advanced manipulation like unfolding and so on. We don't work directly with the depth maps, but what we do at first is that we fuse these depth maps into a single point cloud using a well-known Kinect fusion algorithm. We also subsample this point cloud to 1000 points, which we found to be enough to represent the shape of the hanging garment. It makes the computation less expensive. The garment is processed with a convolutional neural network, the point cloud is processed with a convolutional neural network, which we introduced in this thesis. And the key ingredient, the key component of this convolutional neural network is this generalized convolution for point clouds. So the input of this generalized convolution is a set of n points in a 3D space. Those points are denoted with those p's, and each point is also assigned a d-dimensional feature vector x. At the beginning, this d-dimensional feature vector is just 3-dimensional, and the features are the coordinates of the point itself. But it can also contain the normal or some local features computed for the point cloud and so on. But in our experiments, we only use these 3D coordinates. How we generalize the convolution for these points? So basically, in image, the convolution is usually like so there is some convolutional kernel which is for each pixel we take its neighborhood and we multiply it with this convolutional kernel and sum it. And we do something similar for point cloud here, meaning that for each point we find its k nearest neighbors, including the point itself. So here in this case we found 3 nearest neighbors, and we concatenate feature vectors of these nearest neighbors to a feature vector describing the whole neighborhood of the point. The feature vectors are concatenated in ascending distance from the reference point. So here for point P1, we would concatenate this feature vector x1, then x3, and x4 to describe its local neighborhood. Then we compute dot product of this feature vectors describing neighborhoods with something which can be seen as a convolutional kernels. And we use m convolutional kernels, and if we perform this convolution, we get for each point a new m-dimensional feature vector. A special case of this knn-conv is knn-conv for k is equal to 1, which means that basically for each point we don't find any neighbors, we just take its feature vector and we convolve it, meaning that we compute these dot products for the feature vector itself belonging to the point. This performs basically some feature transformation some transformation of the feature of that particular point. And this special case of our knn-conv is this is the computation which is used by quite famous point net, which was basically the first network for dealing with point clouds. So our generalized convolution is a generalization of this initial point net method. The third key component of our network is subsampling the point cloud. After processing the point cloud with few convolutional layers, we randomly discard usually half of the points and the feature vectors. We do it because we want to reduce some redundancy in representation of the point cloud. As I told you, since we for each point we find its nearest neighbors, and we concatenate the feature vectors for these neighboring points to describe the neighborhood. The neighborhood descriptors for neighboring points are somehow redundant. They share some components of these feature vectors are shared, and so we can discard some of them. It helps us to reduce the computational cost and also improves the robustness of the network, because it can be never sure which points will be discarded. So we force it to learn more general representations of the neighborhood. This is our final architecture, which we call knn-net. You can see that on the input there is 1,000 points, 1,000 three-dimensional points, and there are 3 convolutional blocks. Each convolutional block is formed by this knn convolution over some local neighborhood. The local neighborhood grows deeper in the network, so it starts with 4 neighbors and grows to 12 neighbors in the final architecture. Then this knn-conv is followed by this special knn-conv for k is equal to 1, which is this feature transformation, this extraction of higher level features. And then there is a subsampling. So after each block, the size of the point cloud is decreased to half. In the end, as you can see on the right side, we get there are only 128 points remaining, and for each point has 500 dimensional feature vector, and we perform max pooling. We apply max pooling over all these points to aggregate these feature vectors to a single global feature vector describing the whole point cloud. This global feature vector is then classified with this type of fully connected layers. Since we don't have enough training data, we don't have enough hanging garments to train this network. We train it instead on ShapeNet, which is a large public data set of 50,000 mesh models over 55 categories. For this sample, 2,000 points for each model from its surface. We normalize it, and we use it to train the network. We use two augmentations while training the network. We have each sample represented by 2,000 points, but in each iteration, when the sample is presented to the network, we sample only 1,000 points or these 2,000 points, so that the same sample is never represented. It's never represented by the same set of points. And we also rotate the samples randomly around the vertical axis. So, as I said, we train the network on this ShapeNet, and initially I wanted to do transfer learning. I wanted to use I wanted to retrain the fully connected layers for garments classification, but since the data sets of garments are pretty small, in the end we don't retrain the fully connected layers, but instead we use only the global feature vector extracted by the convolution layers, and we train a linear SVM on top of it. Here you can see the evaluation of our method on a publicly available data set of hanging garments containing 700 samples. You can see that we sort of achieve state-of-the-art results. I must also say that so the first method is based. Both methods are based on depth maps as well, but they don't merge the depth maps into point clouds. They classify using the depth maps directly. And like one drawback of these methods compared to our method is that it's probably not wanted. So it's quite possible that these methods don't classify only based on the shape of the garment in the depth map, but also on its size, because the depth maps are acquired from the constant distance. So smaller garments take smaller part of cover smaller part of the depth map. Since we normalize the point cloud, we only classify based on shape. So let me summarize my contributions of the thesis. As I said, I dealt with 3 topics. The first one was visual perception of garments for the robotic folding. Here I introduced this automated segmentation or automated initialization of RepCut. I introduced polygonal models which describe the contours of the garments, and I developed 2 methods for matching the models to garment contours using either the mentioned local cost or the more complex global cost. In the field of visual perception of garments for their robotic unfolding, I formulated the problems of detecting folded layers as an energy minimization problem combining both image and web data, and I introduced these heuristics for estimating folding axis and checking the virtually unfolded garment. And in the field of classification of hanging garments, I introduced this generalized convolution, which is applied on point clouds, and I developed and trained this KNN net architecture using this convolution operation. Thank you.
Okay, thank you very much for the presentation. I think it was a little bit longer.
I was surprised by the impossibility to.
Sure. I will postpone all the discussion to the presentation itself to a later stage and ask the reviewers first to present their reviews. Each of you had enough time it's possible to split the questions to two parts, something asked now, some can be asked later. So it's fully up to you how you split this. What is important is to address your main criticisms in your review so that it's clear that we have somehow discussed those and possibly looked at whatever is criticism. I would like to ask Dr. Jančar to start with this review first.
Please, thank you. So I should first say a few words which are not explicit in my review, yes, because when I was appointed, but I asked to be a reviewer, it was clear, I clearly said that I am not a specialist in this area, but I was assured that the other reviewers will be well-known experts in the area, so I took my task as on more general level, so that if I am teaching theoretical computer science and working in theoretical computer science in another university in Czech Republic, so I try to make to convince myself if the student has demonstrated that he was doing solid research and achieved significant scientific results. Yeah, so and if his PhD thesis meets the usual requirements on solid universities in the Czech Republic, yes. So my review is on, so to speak, more general level. I have no real technical questions, yes, because I understood that the topic of the thesis is a part of interesting international research, which was documented also by involvement of the author in the recent European project, which he mentioned. The thesis was fulfilled in this way. This I mainly estimated by the fact that his publications were given at solid high quality conferences in this area. Yeah? So this was a sign for me that his results were given some was on a solid level and was somehow approved by the community, scientific community in the area. Yes. So the elaboration methods, his work is written in, from my point of view, in solid English, and gave me the nice overview of his efforts. Yes, and he writes in confidence about the methods in the area. So he knew them, he knew how to apply them, and he developed some novel modifications and combinations. They are suitable for particular task he is solving. Yeah, so the results, as I say, were important for me, was that they were published in solid venues. He was also participating in a journal as a co-author of a journal paper, and I do not doubt that his contribution, his personal contributions, were significant. Yes, it was also given by some percentages, and I had no doubt that his contribution was sufficient. So, as on the whole, yes, I find it very nice quality work from my point of view, and when I compare with PhD thesis, I know at other universities and so on, so I have no hesitation to recommend this thesis to be defended, yes, because the author, from my point of view, has demonstrated his ability to pursue high quality research, also as a part of an international team, and all this is testified by his publications in the renowned venues. Yes, so my final recommendation was, I recommend the thesis to be defended, and I had not formulated any particular questions in the review. Yes, so that's for thank you.
Okay, Okay, thank you very much for a positive review. Of course, there will be more time for questions.
Yes.
After we've seen the presentations. So we can proceed with more questions later. Okay, so if Dr. Aragon Caramasa would like to continue, please. It's your
Yes.
floor.
Thank you. Just to get some, no questions now, questions are going to be later, right? Technical questions and...
You can do it in two rounds. First, more pressing questions now, after you summarize your review, and then there'll be additional time for more discussion after the review started.
Okay, perfect. Well, just, I concur with Dr. Janker. The thesis is novel, well written, but in terms of, I don't doubt that there's a novelty within the thesis, and because it has been published in well venues, in conferences, journals, and there's a clear novelty within it, and more importantly, there's a demonstration, real demonstration in a robotic system, which is a hard task. I appreciate that. So, well, I will start my review. The thesis is essentially on trying to understand how visual perception can be used for robotic manipulation of garments. Well, I did enjoy reading the work, but I was not convinced by the quality of the write-up in the thesis. But that is essentially that there are few grammatical errors, they are missing punctuation marks and typos, which reduce the quality of the thesis, especially for a PhD standard. And well, I will go now chapter by chapter just to give a high-level discussion and some questions that are quite pressing. To begin with, in chapter 1, the chapter introduces the problem, challenges, and the underlying motivation why we need visual perception for manipulating the following objects. However, I wasn't clear on the hypothesis and thesis statement of the overall work. So, in your presentation, you have the contribution, everything fits together, that's clear. But what will be the thesis statement in your thesis? Or if there's one?
Well, so I think that in this case it's difficult to say like one thesis statement. So like in general the thesis statement was a development of perceptual methods for handling a garment with a robot. And since I introduced three quite different methods for different tasks, I'm not able to say like nothing else than this general statement. So we wanted to explore this interesting research field of handling the garments.
Okay, that's fine. I'll move on. In chapter 2, you provide what is a snapshot of the state of the art over the years, because the project started in 2012, so I'm aware that the state of the art back then was completely different from what it is now, especially with the elements. But without removing those considerations, the main issue I found in that chapter, insights on the issues. What were the issues back then, and how do you inspire your developments based on that literature review? But it was not a question, it's just a comment part of the review. And so moving on to chapter 3, I have a very specific question. You demonstrate that how the visual perception can be addressed or can be used for folding in a real robot. But within your experiments and the description in your chapter, it's not quite clear how do you choose the parameters. And it seems that it's not grounded on experimental evidence. Well, would you like to expand on it or explain it? Probably I missed something in your dissertation.
Yeah. So yeah, you are you are right that there was I didn't perform any end-to-end experiments evaluating all possible combinations of the parameters. But I think that on the other hand, I think that all parameters are specified somehow. So here I listed most important, or basically all parameters of the procedure. So the first parameter is the number of components in the model of background and foreground color. So here I use 3 components. This was based on visual inspection of the RGB space, and also since we use this modified GrabCAD algorithm, there they use 5 components for background and foreground models, but they also work with general images, and this is quite a restricted subset of possible images. So I use 3 components. Then there are thresholds on likelihoods for the initial background segmentation. So basically, we, as I said, we classify each input pixel in the learned background model to get the coarse segmentation, and then we set basically 2 thresholds, and these thresholds are set so that 80% of training data, meaning 80% of real background pixels, are classified correctly in this background model. 3% are misclassified as foreground. We assume that there is like 3% noise in the training data, and the rest are unknown. And these are used to get the initial coarse segmentation. So again, this was not tested like end to end, but it was basically like I tested the segmentation separately from the other bugs. I didn't perform any end-to-end experiments testing all the possible combinations of the parameters. The third important parameter is the number of points forming the simplified contour. And here we use for model which has m vertices. So for example, for towel there are 4 vertices, 4 corners of towel, and we, while approximating the contours extracted from the segmentation mask, we use this n is 4 which is 4 for towels plus 10 to get the approximation of the contour. We do this because, as I said, we are not sure where the real vertices are, so we want to get some approximation. And for lower values, we missed some vertices, and then it's not possible to match the model. And larger M makes matching unnecessarily slower. So this was set empirically on the training data. And then there are weights of the matching costs, and they were set empirically on training data to balance typical values of these costs seen on the training data. So they were set, as you can see in the presentation. So this would be my answer to your question.
Okay, thank you very much. That's clear. Okay. Well, I'm just curious. Yes?
Excuse me, am I allowed to ask questions regarding this as well?
Yeah,
Yes.
please do so.
So I had the same impression that you didn't really report it in your written thesis how you have chosen all these parameters, and for now it's still not clear for me how you picked those parameters. So they seem like being chosen ad hoc now. Did you test several parameters there, or did you just pick them and hope for the best? Of course, I understand your explanation that we want to get in a certain regime, let's say, but why not taking 85% for example, of the training data, or taking 20 and n plus 20 model vertices. So there's no comparison given in your thesis, in the written thesis at least, that validates this particular choice.
Yeah, so I tested different values of these parameters, but again, as I said, I didn't do this end-to-end comparison. Like for each stage, I chose the parameters which were working for this particular stage.
Okay, but even this was not really reported in the thesis that you consider different values and you didn't report the different results, for example. So this conveys the information that might be you just have chosen them ad hoc, and that's of course bad for scientific contribution.
So as I said, I always chose them from different.
Yeah. So I got that, and thanks for this clarification.
Thank you.
Okay, I think we can continue with the second review.
Okay, well, I'm just curious, why did you choose to use cyclic operators for the vertex and those ones?
Yeah.
Choose that notation instead of just standard notation. Well, simple notation.
Yeah. So I chose so these circular operators, which I call cyclic addition and cyclic subtraction. I use them to simplify the description of the matching costs and of the costs basically. So you can see in the image if I want to, because the input counter is a closed polygon, and if I want to reference next point for the point P4, I can write normal +1. But if I want to reference next point for P7, it's because it's closed is the first point, and P7 like 7 + 1 is 8. So that's why I use this cycle parameter to be able to easily reference the neighbors in this closed counter. But I agree. You said that this is used in Hilbert spaces, and maybe it might be confusing. On the other hand, the operators were defined in the thesis, so I hope that there is no confusion. But I agree that it's maybe non-standard.
Okay, well, thank you very much. I'm going to move on to chapter 3. And well, my main concern in this chapter is that it's mainly a review of published work of the authors. My main concern there is that what was your contribution? It's clear, if I accepted your dissertation, I can see what is your contribution. But what is the meaning of that chapter? Why did you include it if it's not really entirely your work?
So you suggested in your review that this chapter should be probably moved to state of the art, or it should be somehow divided into different parts and moved to other parts of the thesis. Of course, since we don't have this system of submitting the thesis at first and then submitting the corrected review, I agree with you that it would be better to do it like that. My motivation for doing this was that I wanted to show my method for the visual perception method for folding, and I wanted to show it in. I wanted to show how it performs while incorporated in this whole pipeline, and I also wanted to show the experiments evaluating the whole pipeline, including this folded method for estimating both of the unfolded and partially folded garment. And so this was my main intention.
But that leads me to my follow-up question. How did your system perform within the system? With the overall pipeline, sorry.
Yeah, so I don't have a slide prepared for that, but like it's summarized in the chapter 4 how it performs. There are experiments provided there evaluating individual parts of the pipeline, and as far as I remember, not we, because I didn't perform these final experiments, including my method, but it was performed by other group in our project, and they evaluated the pipeline on, I think, 96 samples, and this procedure for folding, it failed 9 times out of these 96 samples, but only twice it failed because of the visual procedure, and 7 times it failed because of the robotic manipulation for folding. And it failed mainly because since the space of the space where the robot can operate, it's quite limited. Usually the failure is because the garment is placed in such place that cannot be reached by the robot, and it's not possible to plan a folding move. So this was the main source of the errors. And again, as I said, there are 2 failures of the perception part, and the difference between evaluation as a part of the pipeline versus evaluation of the folding itself is that there is unfolding performed prior to folding, and of course the accuracy of the folding is affected by how well the garment is unfolded.
Okay. Thank you very much.
I agree that it would be probably so. Despite that, I state at the beginning of chapter 4 that it's not my contribution. It just describes other methods so that we can evaluate or that they can evaluate our method in the pipeline. It's probably not standard, and I should have done it in a different way.
It would have been better to have this chapter as a background or as a use case rather than being a full chapter. So it was a use case of the approaches that you have developed. But yeah, that's completely fine. Thank you very much for your answer. Sure, there's going to be more technical questions about this chapter later. So I'm just going to keep moving for the review. I'm just covering the high-level aspects of it. In chapter 5, I did enjoy reading this chapter specifically, and I think makes the conditions of scientific writing over comparing with other chapters. My only question here is that there's the critical analysis of the failure cases. You present the results, but you don't analyze them.
Yeah. So.
Per se. Would you like to expand on it?
And so basically, I think that there was some analysis provided. Maybe it was not detailed enough, but I described in the thesis that the wrong labeling of pixels, and I provide this qualitative evaluation of these failures. So these are the images taken from the thesis. So the first source of failures is it's a failure in the labeling procedure, and it can happen when the depths are too noisy, or when they are, as you can see in the left and middle image, the depths are pretty noisy. So I think that you cannot see my pointer now. So the depths or heights which correspond to the top folded layer are somehow equal or similar to heights so there is like strong noise, and this makes the procedure to fail. And here for the skirt, the procedure was the the boundary of the layer should be shifted a little bit, and yeah. So it's difficult to evaluate. So there is some minimization of some cost, and if the costs so it's like I don't know how to further evaluate it. So it's basically energy minimization problem. There are some costs defined, and if the data are too noisy, the procedure fails. And another source of failures is it also happens that all pixels are aligned to the same layer. Those are the top two images, and you can see that again in the height image, all pixels appear to have the same height. So if data like this are given to the procedure, the costs are set so it's like the procedure fails. And the third case of failures is this wrongly detected folding axis, and this can happen because we use, as I said, we don't use any model of the garment, and we use these heuristics on detecting this folding axis. And this heuristics doesn't work it's not like general enough heuristics, it doesn't work in all cases, so this causes this 2% failure rate.
May I ask a question?
Yeah.
What was the source of that data? Was it the Kinect?
Yeah, it was Kinect.
Now, after you know the analysis of this, would you have any recommendation on how to do the depth sensing in different ways?
Yeah, so I think that so it would be possible. So there are no. I think there are generally problems with features. So it's quite difficult to use structure from motion for this, even though this structure from motion sensing was also developed as a part of this. But by the way, it was developed by Dr. Camarasa. So we also had this data available. In the end, we decided to use, because it was like simpler to use the range sensor than using.
So,
And it was
Canon has two cameras, no? Or three cameras? Projector and two cameras.
yeah. So here we used the Asus Xtion. So it was not Kinect, it was Asus Xtion, and yes, it's structured light. The newer Kinect was time of flight, but this was structured light.
You could use the stereo, the estimate of the depth map from the device itself, and initialize a stereo connotation that would be using a model which is adapted for flat pieces, perhaps. Is that something that could be thought of?
I'm not really expert in this, also in 3D, in stereo vision, so I'm not able to comment on this.
Thank you. Sorry for interruption.
No, that's completely fine.
And
Thank you very much.
sorry, and you also asked about the manipulation failures, and again, as I said, so like it would be possible to post the garments in such configurations that we wouldn't be able to fold a single garment. If you like put it far away from the robot, then the robot is not able to reach it, and it's not possible to unfold it. And the other hand is the other thing is that while we are performing these experiments, the robot was also used for other projects. So only one arm was equipped with the gripper suitable for grasping garments. So this even decreased the possibility of unfolding the garment.
Okay. Well,
And
thank
Sorry, and one more thing.
Yes.
We also wanted to provide more examples of failures for skirts. So again, there is nothing special on skirts. Again, the procedure can fail because there are like strong visual edges in the image, or which are not edges aligned with the boundary between the layers, or the depths are too noisy, and then the layers detection fails. So but there is nothing special about skirts.
Okay, but so in a nutshell, what will be the main limitation of this approach?
Yeah, so the main limitation is that, of course, the thickness of the garment, like thickness of the layer, must be at least somehow visible in the depth map. For example, if the garment was made of silk, it wouldn't be possible to unfold it like this. So this is one limitation. And yeah, so it only works for these thick garments. Another limitation is that, as I said, we don't use any model of the garment, which of course simplifies the things for us. But then the phonic axis must be, or not must be, but we estimate it using these heuristics, and the heuristics can also fail. So to deal with this, like using a model of the garment, it would definitely help. So this is also like limitation of the method.
Okay, what would you do, or what will be the future work? What will be the next step to address all these limitations, in your opinion?
So I think that introducing a model here would help a lot. So this would be probably like model of the garment, probably. Like, it's quite, but on the other hand, it's quite difficult. So here, as I said, this is based on the detection of the top and bottom layer. But this task could be also approached in other way. We could model the shape of the garment, and we could estimate, and it was in fact it was done by other researchers. We could try to so we could have a model of unfolded garment, and we could try to estimate how the model needs to be folded in order to match the data, and maybe somehow combining this. So because these methods are on the other hand based only on images, they don't use depth maps. So maybe then combining the image and depth information with these models, that could be pretty interesting.
Okay, thank you very much. I can actually stay on that chapter for a long time. So in the interest of time, I will move on to chapter 6. That was an interesting approach. Understand how point clouds, especially for the formable objects, can be modeled with deep learning. And I think there's a lot of novelty in it. It is significant with respect to the state of the art. My main concern is the experimental section, which falls a little bit short in terms of presenting an in-depth evaluation between your approach, K and N, with the state of the art, especially on PointNet, for example, how well does it perform, and also on the ShapeNet. Yes, because from my review, I remember there's you designed KNN-Net to be compatible to ShapeNet, but you don't evaluate ShapeNet in your use case. What was the limitation there, or what was the rationale for not doing it?
Yeah, so I tried to use PointNet. Unfortunately, I don't have the numbers. I cannot present the numbers because I didn't include. at the beginning, I tried PointNet and it performed worse on the garments than this, but I don't have this data anymore, and so I just knew that it performed a few percent worse than this KNet plus linear SVM, and it was so here I evaluated with like 3 state-of-the-art methods, and it was like worse than these two, but I cannot provide the exact number because I didn't have those numbers anymore. Yes, and I agree that this should have been probably included in the thesis, and maybe I should have also included evaluation compared. So I somehow thought that it's enough to compare with the state-of-the-art methods on this specific task, and I didn't include other methods than this one in the evaluation, than this KNNet. But you also mentioned this shape net. So what I did is that I evaluated our KNNet. So just to clarify, the ModuleNet and ShapeNet are not architectures; they are data sets. So ModuleNet is data set of approximately 12,000 samples over 40 categories, and ShapeNet is this data set which we used for training our KNNet. So both these data sets they don't include garments, but they include they include those general objects. And KNNet is so like the final architecture which I choose is worse on ModuleNet than PointNet and PointNet++. But on the other hand, it's better on ShapeNet, and this is most probably because the PointNet was trained on ModuleNet, and PointNet and PointNet++ were trained on ModuleNet and evaluated on them, and they were selected. So the architectures were selected so that they perform good on this ModuleNet dataset. On the other hand, I used ShapeNet dataset because I didn't really want to achieve good performance on the ShapeNet dataset or ModuleNet dataset. I wanted to train features which are good enough, which are good if we transfer them to a different domain. So I chose the architecture which was performing well on ShapeNet, and it performs worse on. Of course, I train on ModuleNet, but I use the best architecture on ShapeNet. And if I take PointNet and PointNet++, which are aiming on ModuleNet, then these architectures, while trained on ShapeNet, they perform worse than our architecture. And as I said, I remember that I tried to evaluate PointNet trained on ShapeNet and to use it as features, but I don't have the numbers, and I didn't include that in the thesis because I didn't evaluate our task using different methods than those which were specific for this task.
Okay, well, sorry, actually that was my misconception. For some reason I was thinking that ShapeNet was an architecture. Thank you for the clarification. So yeah, you answered my other questions, so fair enough.
It's a little bit misleading. There are too many nets.
Yeah, too many nets, and but yeah. Okay, well, let's move on. The final chapter. Actually, I don't have a specific question there. It's just that your conclusions chapter is very light, and there is no critical elaboration on future work. And again, I would like to hear what will be your future work and your ideas for future work. What's next? After you have done all this work, and if the European Commission gives you 1 million just to focus on this, what would you do next?
And so maybe what was not mentioned or maybe I mentioned it in interaction, but like me and my supervisor, we were really, or maybe my supervisor, Professor Lodge, he was really interested in modeling the garment under manipulation. So let's say that we start with a crumpled garment laying on the table, and we would create some model representing it, and this model would somehow combine description of what is visible at the particular in the particular moment with some estimation what is not visible, and then the robot could act so in such a way that it learns more about the invisible part. So refine the initial model by manipulation. So and we are thinking about that, but I was afraid of this task. Like it seemed to be too difficult, and I didn't see any ways how to approach it. So we didn't do that. And then in the conclusion, I also say that maybe it's like too general, but what I think is really needed is improving robustness of the methods, because most of these methods are too fragile, and then if you connect multiple methods into pipeline, which was done in this Kopema project, then there are the first the unfolding part can fail, the folding part can fail, and we should make it somehow more robust. We should include some fail-safe strategies to restart some stage of the pipeline, or maybe start again from the beginning. So this will be also interesting.
Okay.
And
well,
then
thank you very
maybe
much. Yeah.
maybe something more specific. So I got really excited by this, say, geometric learning, applying neural networks on geometric data, and not only on point cloud, but also applying neural networks on meshes. And this is very interesting field of research these days. So maybe this will be the like more concrete way what to do, more concrete thing what to do.
Okay. Well, thank you very much. I think that concludes all my my summary. Recommended in my review that the author have shown the ability to perform research and achieve scientific results. And I recommend the thesis for presentation, subject for some corrections in the dissertation. But well, that's me. Thank you very much.
So I would like to thank you for the review, and I agree that your objections are valid, and if they were included in the thesis, it would improve the quality of the thesis. But unfortunately, it was not possible because we don't use this two-round system.
Okay, so thank you very much. I think we have the last review, Dr. Haschke. His life will probably be a bit easier because some of the criticisms are similar. But anyway, take your time, please, and do it as long as you do.
Yeah, thank you very much. I agree to a large extent with the reviews from Mr. Camarada, right? So I think Mr. Stria tackled a lot of interesting questions and also pressing questions for manipulation of deformable objects. And yeah, you collected a lot of different methods from different areas in order to really solve this or contribute to the problem of manipulation of these garments in this project. And what you achieved is really impressive. But I was kind of disappointed, much like the previous reviewer, how you have summarized all this information. And because that's the approach and that the candidate can improve the thesis, I made a lot of suggestions in my review how to improve the thesis in one or the other direction. So I won't go into these details because here we just need to decide whether the candidate or Mr. Stria passes or not. I think that's rather simple. So I never had any objections. I think that the thesis is high quality enough to pass such a defense. So I recommended that clearly for presentation. But yeah, let's go maybe to some interesting questions I had in a similar fashion as Mr. Camarada did. So let's go chapter by chapter. I agree with the previous surveyor that the state-of-the-art section was, you kind of listed a lot of different methods, which is of course good, but you didn't discuss the pros and cons of those methods. So as a reader, you don't get an additional benefit of reading this apart from summarizing that. It would have been nice if you could have judged all these methods or grouped the methods, creating taxonomies of those methods and so on. So I don't have 3 questions regarding this chapter, so let's go on to chapter 3, which was the color-based segmentation and the contour matching. I do have some concrete questions here regarding the contour matching. So you essentially propose 2 methods. You call it local and global. Maybe can you summarize once again, or where do you see the commonalities between these methods and the differences?
Yeah, so as I said, the local matching cost is it uses simpler costs which can be evaluated easily. It's easier to evaluate them, and then the dynamic programming algorithm is simpler. Whereas while we use the global costs, we also mentioned that maybe the local and global is not the best naming, that I should have chosen a different naming, but I'll continue using this naming because it's written in the thesis. And by the way, the motivation for this global cost was mainly the vertex matching cost. You can see on the left that while evaluating the the vertex matching cost on the left, which is the local matching, is assigned, is paid for the pixel, the point pj being mapped to vertex vm, and it's based on the learned inner angle adjacent to this vertex. And here, if you want to measure the angle in the contour, you measure it from this local neighborhood of the point pj, as you can see on the left image. Whereas, which is like local measurement of this angle. Whereas in the global variant of this, we measure the angle based on the point which is mapped to the previous vertex and mapped to the next vertex. So this is why I chose this naming. And also, in addition, that there is also this cost based on the relative length of this part of the contour versus the relative length or learned distribution of relative lengths in the model. So the procedures are so both algorithms are both methods are quite similar, but since the costs in the other case and the second case are more difficult to evaluate, also the dynamic programming procedure for matching them must be more difficult. And here, these are also the images taken from the thesis. And here I tried to show, because it's described somehow in the algorithm, but I also wanted to show how the minimization works and why we need to use why we need to use the more complex algorithms for while using this so-called global costs. And you can see here that, sorry, you cannot see my pointer. So TIM is the cost of mapping points P1 to Pi to vertices Vi, Vm. And it can be, to find this optimum cost, we can use the previous costs of matching the previous points to the vertices V1 to Vm minus 1. And this is basically that dynamic programming procedure. So while trying to optimize this cost, we try to match different points to vertex Vm, and we use this previously computed costs. This is how the dynamic programming works. On the other hand, this global cost, it's not possible to do it in this straightforward way, because there is this global vertex matching cost which tells this is Vijkm, which is a cost of matching point Pj to vertex Vm, provided that point Pi is matched to the previous vertex and Pk is matched to the next vertex. And this is needed in order to evaluate this to measure this angle in the context, this angle Pi, Pj, Pk. And this makes the dynamic programming more complicated.
Yeah. So thanks for this, Eric. I have some echo here. Thank you very much for this clarification. I think what I missed in the thesis, in the written thesis, is that you indeed measure the angle differently in the global approach as well. It's not just adding the edge cost, which was my conception of the global measure or the method, but you indeed measure the angles differently, and you need to consider all the different angle measurements as well, which extends indeed the cost matrix into a 3D tensor.
Yes, and of course it would be possible to add these edge costs also to the local procedure. It would be possible.
Yeah.
So you said that the same, basically the same algorithm could be used also for global costs, which, as we now clarified, is not true. But definitely the edge cost could be added to this local cost, and then we could use the simple algorithm for evaluating, for finding this optimum.
Exactly. Did you try that? Compare similar cost functions, so and then only the measurement of the angles is differently. Did you consider that as well?
No, I didn't try that.
Okay.
So basically, these two methods they were published. So at first, this local method was published, and then this global method was published, and there were other improvements as these 4D models which I mentioned, and that's why I included it in thesis like that. But they could be also, both methods could be combined together, and maybe this was also. I don't know whether I should comment on this. You said that we could, or should I? Maybe I should let you talk.
So another point, if you want to tackle that now, is that simplify your algorithm by only considering this kind of bandit-like structure because you already know that the neighbors are always connected. So you don't connect any point, but you always connect the next neighbor. Do you want to comment on that?
So, I'm not sure that I understood now. So is it the same question as is shown in the slide, or is it a different? So could you maybe repeat the question?
So my impression is that you need this triangular structure because you need to consider all the possible pairings of associations in a forward path, considering all potential future points, even in the simple approach. But that's, from my point of view, not really necessary. You only need to consider the next one. Don't you?
Not only next one, but I need to. Yeah, like so I don't need next one at that particular moment. I need only next one at that particular moment, but I will need all of them in the end. So basically, so if I want to find the
He doesn't see your cursor.
so if I want to, so it's shown here in the figure. If I want to find the point that should be mapped to the vertex Vm, I know that first n-1 points cannot be mapped to this vertex Vm because these points must be vertex, at least if I use all of these points, if I map them, all of them, I need to map them, so I need to save these points for first n-1 vertices. Again, the last points need to be mapped to the vertices Vm plus 1 to Vn, but I need to check all the points besides, because all these points from m to n minus capital M minus small m can be mapped to the vertex Vm at some point. And this is not, as you said, this is not used in the local matching algorithm. So in the local matching algorithm, I don't use the right side of this figure. So I try all points up to the point Pn, and that's why I was developing this algorithm. I didn't realize that this was possible. So yeah, so it could be also improved there. Included there, it could be reduced to this bandit shape instead of full triangular shape. But on the other hand, while developing this global matching algorithm, this is already used there. And again, so I didn't. This was also one of the improvements of the paper which extended the original paper. So of course this could be also used for the original method, but I didn't use it because I was not aware of that while implementing that method. I'm not sure whether I answered your question. I hope so.
Yeah, I think so. Okay, so let's continue with the chapter 4. My impression again, similar to the previous area, was that it was not clear enough stated that this work is just summarizing, I think, work from others. So being part of the remaining thesis, or being a normal chapter in the remaining thesis, it conveys the idea that this chapter is a similar contribution of yours, which doesn't seem to be the case, right? So your focus was on the perception side, and you just summarized what the other team members in the Kopema project then did on. So that's why I want to ask you for more details. If you already confirmed that it is like this, but the clear statement is missing is that this is not your genuine contribution. Regarding chapter 5,
Sorry, so if I can comment, so of course I should, so at the beginning of the chapter, this is citation from the thesis, I state that I definitely didn't want to include this into my contributions, and it's stated there, but I agree that so I maybe it should be repeated, but not only repeated, I think that the structure of the thesis should have been different. It should be probably included in the related work, or somehow, yeah. So I think that it's stated there that it's not my contribution, but I think that the organization of the thesis might make some you. I am not surprised that maybe you were confused by this.
so we both were confused regarding this, and so obviously it was not clearly enough stated that this is the contribution of others. So it's fine to present this work because it kind of rounds up the whole thesis, and it's also nicely presented. So although you present others' work there, that's why it's completely fine, but it needs to be clearly stated, in my opinion, in such a work.
Yeah.
Let's then continue with chapter 5, which handles the segmentation of folded garments, right? So they essentially applied again this graph cut algorithm from the author, and you slightly modified of course you modified the algorithm to work with depth images instead of color images, but you also modified the Gaussian mixture model learning there in order to consider the constraint that here it's shown already, that two layers are twice as thick as a single layer. So I like this idea very much. Really follow your the derivation of the corresponding update equation, which is 5.14. Because you already looked up the slides, I guess you prepared more in-depth derivation of that.
Yeah.
And I'm still here.
Yeah, so the context is that we use EM algorithm to estimate the Gaussian mixture model with two components. These components have shared variance. They have priors, prior PT and PP, because this T and B, this means this top and bottom layer, and the means of these Gaussians included in the mixture are linked with this relation that the top mean is twice the bottom mean. So there is this delta mu, which denotes the thickness of the layer. And now the E step, it's this follows standard algorithm, standard EM algorithm for Gaussian mixture model. This derivation, and the E step is it's pretty standard. We don't do anything special here. So we build this conditional distribution of pixel Q with measurement with hard measurement H Q being assigned to the layer Z, and we build this posterior distribution. As you can see, the first row. Then we apply the Bayes rule to get to the second row, and since it's a mixture of Gaussians, so these are our general probabilities, and here is how it looks like for Gaussian mixture. So this is standard step for mixture of two Gaussians. And then in this M step, we need to maximize expected log likelihood with respect to this conditional distribution Q shown on the previous slide. And again, this is still as in the standard EM algorithm for EM. So those first four rows are the same as in EM algorithm for Gaussian mixture.
Yeah.
Now it so up to now everything is the same as in standard EM algorithm. And now while minimizing this cost function j theta, while estimating the next best values of the parameters in the M step, it differs while estimating the next means, because the means are linked through this thickness of the layer. So the step for the M step for the means is custom in this case. So to minimize, or sorry, I maybe minimize. So we maximize probability. So we need to maximize. So in order to maximize this expression, which you sorry. To maximize this expression on the third row, we take a partial derivative of it. So we take a partial derivative of this expected value with respect to that delta mu. And if we do it, since it's a mixture of Gaussians again, these Q's they don't depend on this is just like constant for particular Z and particular Q. It's just a value, and this is this prior. Sorry, you don't see my cursor. So there is this PZ, which is a prior. Or on the first row there is this PZ, which is a prior for that component, and then there is this normal distribution for that particular component, that Gaussian. And again, this prior, this doesn't depend on the mean, which means that it doesn't depend on the delta mu. So only this part on the second row, you can see only the only part of the expression which depends on that delta mu, and we need to take partial derivative of this expression with respect to delta mu. And there are two components. There is this top component, so one Gaussian for the top component, other Gaussian for the bottom component. And then on rows 3 and 4, you can see the partial derivatives for these two components. So if we use that, this mu t, use this mu t, then mu t is equal to twice delta mu, and we need to take partial derivative of this hq minus twice delta mu to the power of 2, and the partial derivative is 4 delta mu minus 4 hq. And if we take the partial derivative for the other distribution for the bottom layer, we get as a result 2 delta mu minus 2 hq. And if we combine everything together, if I use the expression from the row 2, and I input these two partial derivatives into this expression, I get the partial derivative of the whole expected value, which we for shortness we denoted as h theta, and I get this expression. So on the last row, you can see the partial derivative of that expected value with respect to that delta mu. Now I need to set this derivative equal to 0 and solve for the delta mu, and I get this result.
Okay, thanks for this clarification. Very nice and clear presentation. Was just missing in the thesis.
Dr. Haschke, may I ask an additional question here?
Yeah. Of course.
So if I understood the explanation, without reading the thesis, you have like the maximization step is a constraint optimization, basically, perhaps with substitution. You estimate the expectations without the constraint.
No. Oh, it's EM algorithm. So like EM algorithm, you try to so you have some observed variables and some unobserved variables, and you would like to maximize, and you have some distribution of all these observed variables and unobserved variables, and you would like to maximize log likelihood of these.
Yes.
And
do you have a constraint, or is the constraint included already in the expectation?
Yes, the constraint is included there.
Okay, so I understand.
So it's not like constraint optimization, and
Okay.
you just instead of so the difference here is that if you have two Gaussians in the mixture with means that are not linked together, you would optimize them individually. So optimize take the derivative of with respect to mu1 and with respect to mu2.
I'm talking about the expectation, not the optimization. Expectation is a separate step in the algorithm from
Yeah.
the maximization. The maximization is clear to me, at least I think so. But the expectation I didn't capture. The expectation, what is the expectation is the same as for the same case without the constraint, or not?
So the constraint
The
is
constraint is that the second delta is twice the first.
yeah.
So is that used in the expectation somehow?
Yes, it's used there, but like there is no difference. So in the expectation step, it's used there, but
Okay.
it's not.
In the end, you are lucky enough to have no difference. Is that what you say? Because I can imagine that if you have more complicated constraints, your expectation will have to work with that, and it may be more difficult than without any constraint. Here, you may be lucky enough to, due to the linearity perhaps, or the constancy of the constant, that there is no problem. Is that what you are saying?
But this is related to the maximization step. I think that
No,
for the expectation step, but you just need to build this conditional distribution of the unobserved variables, provided the parameters of the model from previous step.
Okay. Thank you.
So
Yeah, I think it's not.
the means are linked in the expectation step, but it doesn't make it any
It
different.
doesn't play a role in the expectation.
Yes, definitely, yes. That's exactly as it is.
Thank you. Sorry for the interruption.
That's fine, thanks. My next question would be, as far as I understood, you only considered the depth information here. And looking at the failure cases, which we have seen just before, it's, for me at least, obvious that it would make sense to consider not only depth information, but also color information. So how do you think we could combine color and depth information here in order to improve the segmentation result?
So I model the height of the top layer and the bottom layer, and I don't think so. I use the depth to model the height of the top layer and the bottom layer, and I use image to I use image to for the pairwise cost, but not for the unary cost. And I don't see any way how to model the color of the. So why should the color of the top layer be different from the color of the bottom layer? Well, it can be, yeah, that's true.
In the binary cost, you consider the color?
Yeah, the pairwise cost considers the color, but the unary cost doesn't consider the color. And but it's true that it would be also possible to model the color of the top layer and the color of the bottom layer, and there are definitely some cases in which it would make sense. I didn't do that.
If I may, I would comment on this. Texture could be different because the texture orientation is different, considering the cloth, which is directional texture. The directions are different in the field, so perhaps that would help instead of color.
Yeah, so instead of using color, I could use some texture descriptors and yes, and include them in the cost.
Okay, thanks. Let's finish then with the last chapter, number 6, which, in my point of view, poses the most interesting and giving contribution of your thesis, namely the development of this KNN net. Yeah, looking at your evaluation, so I also had some difficulties with your evaluation. So it would have been, for example, nice to have seen this comparison here of these KNN and PointNet methods on these larger data sets. So in the thesis, you only considered, well, in the written thesis, you only considered the small cloth data set, which is, of course, maybe difficult to judge because you might not have enough training data. So here, these model and shape nets data sets are much larger, and here we essentially see that you achieve similar performance, but you don't really also outperform. So then this poses the question, what is really the benefit of your methods compared to the existing methods? Where do you see the strong improvement, let's say, over PointNet?
So clearly there is no improvement on the PointNet data set. Even though, as I said, this comparison is a little bit weird because PointNet and PointNet++ are architectures which were selected to be good on ModulNet. KNet is architecture which was selected so that it's good on ShapeNet. So yeah, and here, as I said, at the beginning, I tried to use. So it seems to me that PointNet is really.
So obviously, functionally, they are very similar.
Yeah.
So we cannot really compare on these accuracy results because they are similar. But maybe algorithmic, like, do you see any benefits of your approach compared to PointNet?
So I think that the benefit of my approach is that I generalize this convolution over the neighborhood. In the original PointNet, each point is processed separately, and then there is this pooling over of points in the end. In PointNet++, they again process each point separately, but then they group neighboring points, and they extract this semi-global features over this neighborhood. So it's somehow a different approach. So in my case, the neighborhood is considered in the convolution itself. In their approach, the notion of neighborhood is considered while aggregating features on this neighborhood.
And obviously, you were not aware of these graph CNN networks, which were also developed around 2017. I hope you got a chance, at least you mentioned that before, to look into these methods now. Can you compare your methods, your KNN-net, with those graph CNN methods?
Yeah. So obviously I didn't do any comparison, but as you said, they are quite similar. So for example, this, I think it's called graph CNN. It's so basically they also generalize convolution on the graph, and they assume that the graph is already given somehow, but we construct the graph based on k nearest neighbors. But but otherwise, I think that I am not an expert again in this field of mesh CNNs and graph CNNs, but I think that from what I know, the methods are quite similar to my method, provided that they both work somehow on graphs. Their method is those graph CNNs are more general because they work on arbitrary graphs. But of course, this method will also work on arbitrary graph. But I constructed the graph based on k-nearest neighbors.
So maybe let's pose the question a little bit differently. As your method is based on the k-nearest neighbors, in contrast to the graph CNNs being based on the graph structure, which is typically a mesh structure, for example, if you consider point clouds, where do you see benefits and disadvantages maybe of one or
I don't think that I'm able to comment on this, so there are I didn't do any comparison, and I'm not able to comment on this, like whether this is better or worse than other methods.
Okay. Let's have a look then. What is my last question? So one central comment I have to chapter 6 is that you decided for a normalization including zero mean, which is of course fine, but also whitening. Can you explain why you decided for whitening? So centering centering and doing a unit ball of your data. So because you essentially lose, for example, the structure that trousers are typically longer than t-shirts.
So, in fact, I don't do this. I use isotropic scaling. But probably I explained it wrongly. I don't think so. So basically, what I do is that I take the point cloud. I find the mean of the points, and I translate the point cloud to zero mean. And then I found the point which is furthest from the zero, and I divide all coordinates of all points by this distance of this furthest points. So the point cloud is scaled isotropically, and it's located. Of course, if I do this, it's located into zero-centered unit ball, but it doesn't span. On the other hand, I don't claim in the thesis that it spans the unit ball, but probably this formulation was not enough to. It was too vague to understand that the point cloud is scaled isotropically. Because as you said, it would be silly not to do it like this, because I would.
Yeah. So from your formulation that it spans a unit ball, I just concluded that you indeed do a complete whitening, so anisotropic scaling. So again, this points out that you need to improve the precision of your formulations when you are writing in order to convey all these details. And I think this is my main criticism, that you have chosen sometimes too sloppy formulations. But yeah, thank you very much. Maybe during my conclusion, I took a note. So you mentioned in the previous comment, in the comment to the previous reviewers question to the conclusion, what's next? What is your next point you want to tackle? You mentioned that you want to improve robustness. A big important and valid point. Do you have concrete ideas on how to improve robustness?
So I'm not working on this topic anymore. So I don't really have these first steps. But again, like improving robustness. I think that and we didn't do that in global map project in general, was to detect the failure. So usually the method, if it fails, it does something. So for example, if we estimate a folding axis, but the folding axis is wrong, we fold the garment, and then we match the polygonal model to the folded garment again. And if the garment slides on the table surface while doing it, we are able to find the new placement of the garment, and we are able to perform the next fold correctly. On the other hand, if the garment falls down on the table, we do nothing to detect it, and we just act as the garment was still there. So I think that implementing such fail-safe strategies to detecting that there was some failure, which can be maybe completely unexpected, this would definitely help.
So you claim it's first of all detection of those errors before you can handle them.
Sorry,
Which is fine.
Sorry, I didn't understand.
You claim essentially that first of all we need to be able to detect those errors before we can handle them,
Yeah.
which is valid.
Yeah, and
Okay,
I think that for detecting the failure, you need a different method. So if the failure is that the garment is folded correctly, but it just slides on the table, you can still use the original method, and you can still match the model to it to find the new placement of the garment. But if it fails completely, if the garment, as I said, if it falls down from the table, it's not possible to use this method for matching polygonal model to garment contour to detect this failure. You need to use other methods.
Okay, thank you very much. Looking at the watch, I see we are running out of time, but nobody stopped me.
I think we still have 15 minutes, so if you would like to summarize your recommendation.
So yeah, I already said in the beginning, no objection at all to not having recommended that thesis for presentation for this.
Okay.
And I don't have objection to pass the thesis as well. So that's my summary.
Okay, thank you very much. We are indeed limited by time, so I ask the local members of the committee if there is any pressing question, something you need to decide on how you vote. No? No? Okay, so any more questions from the reviewers in the second round?
No, not from my side.
Not from my side as well.
Okay, so thank you very much. It was a really thorough and long examination. I'm happy about it because the reviews were raising a lot of points, so I think we have clarified a lot of that. I will ask more questions to the reviewers later in the closed session, but at the moment, all I need is to verify that the quality of connection is sufficient to understand everything that is needed I mean, especially the presentation and the question and answers. From my point of view, it was fine in the room. I don't know how was it on the other side? So
It was fine.
fine.
Yeah, it was fine.
All right, perfect. So at the moment, at this point, I'm closing the public part of this defense, which means that the audience is not supposed to stay with us. And also the candidate, I will call you back to leave it like.
Should I log myself out of Teams, or it's not necessary?
I think it's not necessary.
Okay.
And I will log out people who are supposed to be stop the recordings.